In this video, we're going to talk about the idea of even and odd permutations. So you may recall that previously we proved the following theorem. The theorem was that if tau 1, tau 2, tau 3, and so on, up to tau sub r, are transpositions. Remember, that means 2 cycles in S sub n such that tau r minus 1, the product of all of these down to tau 3, tau 2, tau 1. If the product of all of these is the identity, if the product of a bunch of transpositions is the identity, then quite simply, r has to be even. Which is kind of a remarkable theorem, and proving it was a bit of a chore. But now that we have that, we can do something really interesting. So let's take as an example the group S sub 7, and let's let sigma be the permutation 1, 3, 7, 6, 2, 5, 4. I'm just making this up. Alright, first of all, can we write this as a product of transpositions? And I think so. We now have a couple of different methods for doing that. I'll write down one of them here. We can split this 4 cycle into a bunch of transpositions. I think that would go 1, 6, 1, 7, and 1, 3. And then we'll split 2, 5, 4 into two cycles, or 2 transpositions. So 2, 4, 2, 5. Let's just quickly verify that this does what we want, what we claim that it does. So first of all, does this whole product here take 1 to 3? Well, we see that the first cycle, or the first transposition that moves 1, is here. It moves 1 to 3, and then 3 isn't touched after that, so that looks good. Does 3 go to 7? Well, 3 goes to 1. That 1 gets passed here, and then goes to 7. So in the composition, 3 goes to 7. And then 7 goes to 1 here, 1 gets passed here, goes to 6 here, so 7 goes to 6, and then 6 goes to 1. And I think these 2 cycles will work kind of the same way. So you'll notice that the number of transpositions this took was 5 transpositions total. Okay, it is possible to write this as a product, this sigma, as a product of some other number of transpositions. I mean, for example, one easy way to do it, like one very trivial way to change the number of transpositions would be to say, let's just tack on some random transposition here, 2, 3, and I just picked that out of the blue. No particular reason for a 2, 3. So now I've written it, this sigma as a product of 7 transpositions. And I could also write sigma very differently. For example, if I wanted to cover my tracks a little bit, I could take sigma, I could take this 2, 3 here. The one that I have right here I'm going to replace with, and this is going to seem totally random at first, I'm just going to say 3, 5, 2, 5, 3, 5. And I'm going to leave it as an exercise to verify that that whole thing that I replaced 2, 3 with really is just 2, 3. In other words, this replacement that I made here, this set of 3 transpositions, the product of all of those is just 2, 3. I claim that that's the case anyway. Okay, so now I've written sigma as a product of 9 transpositions. And I think probably if we try to write sigma as a product of fewer than 5 transpositions, we're going to be out of luck. But we seem to be able to rewrite sigma as a product of 7 or 9 transpositions, and really by tacking on meaningless pairs of identical transpositions like this one, we could get 7, 9, 11, 13, and so on. We could get any odd number greater than or equal to 5. But we'll never get an even number, and that's a claim I'm making. I'm claiming that we can never write the sigma named above as a product of an even number of transpositions, no matter how long. And I'm going to prove that now. So here's the proof. We already know that sigma can be written as a product of 5 transpositions. So I'm going to use these symbols to represent those. Sorry, those are all taus, they're not just t's. And those taus are tau 5, tau 4, tau 3, tau 2, tau 1. Remember, I'm numbering in this order because when we compose transpositions, we always start with the one on the right by convention in this course. Okay, so let's suppose that sigma is equal to some other product of transpositions. And now, because I don't really have a lot of other good names for transpositions, and I don't know enough of the Greek alphabet to know the letter that comes after tau. Maybe it's upsilon, but I'm really not certain. I'm just going to make up some other Greek letter. Let's call it mu. Okay, mu looks like a U, which comes after T. I wish I had a better reason for picking that, but I don't. Okay, so let's say it's a product of some R transpositions, which I'm calling, perhaps in total disrespect to the Greek language, mu R minus 1 down to mu 1. Okay, so let's say there's R of them. Okay, so I'm supposing that sigma is equal to both of these products of transpositions. Now let's just try the following thing. So let's try this. So much great mathematics just comes from trying something reckless. Because I know that both of those are equal to sigma, let's equate the two of them, because we know that they're equal. Like, we're not just declaring them to be equal, we know that they actually are. Okay, and because these are all transpositions, I could do the following thing. I could multiply on the right. Now watch my pen. I'm going to mark this in blue for now. Actually, let's use green. I'm going to mark this in green. I could multiply on the right by inverses of this transposition, then this transposition, then this transposition, then this one, and then this one. Or actually, I could do that in one step by just doing this. Tau 1 inverse, but tau 1 inverse is just tau 1. It's a transposition. It is its own inverse. Okay, so just as a reminder, for each I, tau I inverse is equal to tau I, because tau I squared is equal to the identity. Okay, now I shouldn't forget to multiply on the right side of this expression also by tau 1, tau 2, tau 3, tau 4, tau 5. Okay, this is kind of bad board planning here, but here's what's going to happen. The left side is going to be this product of all the mu's followed by all the taus in increasing numerical order from left to right. And the right side of my equation, this is the fun part, the right side of the equation, well look, I've got tau 1 canceling itself out, so all of this is going to turn out to be the identity. And then that identity is now adjacent to both tau 2 and this other copy of tau 2. The identity doesn't do anything, so we might as well just ignore it. So I've now got two tau 2's together, so those are going to become the identity, and then the tau 3's, and then the tau 4's, and then the tau 5's. So I've successfully written down in green the red product's inverse. So this whole thing, the right side of this equation is just the identity, because everything canceled out. But look, how many transpositions are there on the left side? Well, there's a total of R plus 5 of them. The R mu's, all of these, followed by 5 more taus. So I've got R plus 5, and these R plus 5 transpositions, their product is the identity. So by the theorem that we proved, this means R plus 5 must be even, because a product of transpositions, that is the identity, has to consist of an even number of transpositions. Well, you may recall from elementary mathematics that 5 is odd, so that means R has to be odd. That deserves an exclamation mark. R has to be odd. So that means, okay, so what was the claim? I was claiming that we can never write sigma as a product of an even number of transpositions, and now I've proven that. I've proven that if sigma is a product like this, like this one, then the number of transpositions in this product has to be odd, can't be even. So what this means is that no matter what, the sigma that we were talking about, not any sigma, but this particular sigma, get my pen tool here, this particular sigma can only be expressed as a product of an odd number of transpositions. It can never be expressed as an even number of transpositions. There we go. But really, in this problem, I just picked out sigma randomly, more or less. and it consisted of 5 transpositions originally. But there's nothing that special about the number 5. If this had been any other odd number, all of this reasoning down here would have still been pretty much the same, all down to the point where I had r plus an odd number here, and that r plus an odd number needed to be even. So the major point here, and this may seem weird that we're so fascinated with this. I think it'll become clearer later why we're so interested in this. But what all this means if sigma is odd, and by odd in quotation marks right now, I mean it's expressible as an odd number of transpositions, a product of an odd number of transpositions, then it's always odd. It can't escape being odd. And for the same reasoning, if sigma is even, then it's always even. There's no way to express it as a product of an odd number of transpositions. And so because of that, I put these in quotation marks, but these are actually official group theoretic terminology here. So odd means that sigma is expressible using an odd number of transpositions. There we go. Sorry about the poor handwriting there. And then even means expressible as an even number, or expressible using an even number of transpositions. And the result that we have here is that a sigma, a permutation in S sub n, can never be both of these. So just to reiterate the reasoning, sigma can never be both. It'll always be one of them, because we know that every permutation is expressible using transpositions. But it can never be both odd and even, because if it were, then we'd have some product of a bunch of taus. I'm trying to remember to put tau 1 on the right. Tau up to tau r. And it would be equal to, so let's say r is odd, and this would be equal to some product of mu's, let's say up to mu s, where s is even. And then if I use the same strategy I used before of multiplying both sides by the inverse of what's on the right side, it's kind of a weird color combination here, light blue and maroon, but I have tau r minus 1, all the way down to tau 2, tau 1, and then the inverse of this would be the product of all the mu's in reverse order. So I'll just do that over here, mu1, mu2, up to mu s. That would all be equal to the identity. And then, well, how many transpositions are there over on the left side? There's r plus s of them, odd plus even, which is an odd number. And by our theorem, the fact that we have an odd number of transpositions equaling the identity is a contradiction. Haha! So that means that no permutation can ever live in both worlds. It's part of this group, the odd permutations, or it's part of this group, the even permutations. And that's that.